Okay, hello everyone. I haven't posted in a while, but today we're going to get started again with an interesting integral involving a function called the floor function. Now we denote this with the following notation. It kind of looks like there's a floor underneath x, which is fitting. And for anyone who doesn't know, the way that the floor function works is it truncates any number that we put into it. So say we wanted to take the floor function of 2.5, we would truncate it down to 2. The floor function of 2.98, we would still round down to 2, but as soon as we get to 3, we then start truncating down to 3. And what's really nice about this function is that it makes continuous inputs discrete. So if we were to imagine what the graph fit were to look like, in between 0 and 1, every input would just get put down to 0. But the second that we step up to 2, we begin to truncate everything to 1. And similarly, the second that we step up to anything greater than 2, we truncate down to 2, like so, and greater than 3, we truncate down to 3. And so we get a discrete set of bars going kind of up along a line similar to y equals x, except much more discrete. So we get a sequence of bars increasing in height as we travel along the x-axis, stuck in these discrete kind of lines of width 1. Which means actually the integral of the floor function is quite easy to calculate because we're dealing with bars. But what you'll notice is that it actually turns into a sum because we're summing areas. And again, that's kind of showing you the relationship between the continuous integral and that being turned into a discrete summation by the floor function. But the integral we're looking at today is not going to be so simple. Today we're integrating from 1 to infinity x minus the floor function of x divided by x to the 4 dx. Now this is a lot harder, I think mostly because we can't look at that and just draw a picture. With the floor function we can, and so we can begin to understand how the discrete nature of it works. But with this we're going to have to take a more theoretical approach, but also because there's not kind of a set integral of the floor function that we can just use all the time. Like any time, for example, that we see cos x, we know it integrates to sin x. With the floor function, we've always got to be a bit creative. In this case, actually, I think the hardest step of the problem is the first step. And it's in recognizing that there's something we can do with the discrete nature of the floor function. And we're going to use a summation, just like we would do to calculate the integral of the floor function by itself. We're going to remember that the integral of 1 to infinity of this function is the same as the integral of 1 to 2 of this function. I'm just going to write f because I'm lazy, plus the integral of 2 to 3 of this function, plus the integral of 3 to 4 of this function, all the way up to the integral from n minus 1 to n of this function as n goes to infinity. And all that we've done here is say that no matter what the function looks like, if we split it up into bars of width 1 and add those bars together, the area under them will be the same as if we just went from start to finish. And that's just something that's true of integration always and that makes sense to us. Now, why would we want to split our integral into bars of width 1? Well, it's because it allows us to know what the behavior of the floor function is going to be. So we know, for example, that within the bounds of 1 and 2, no matter what value of x we put in to our floor function, we're always going to have 1 returned because we're always truncating down. And that means that the value of the floor function in each of these integrals of width 1 is always just going to be equal to the lower bound because we're always just going to be truncating down to that lower bound on the x-axis. So how can we notate this nicely and mathematically? Well, we're doing a sum starting at 1 and ending at infinity, where our lower bound is n and our upper bound is 1 bigger than n, and we're integrating our function x minus n, because our floor function will always take the value of the lower bound in this case, divided by x to the power of 4 dx. And this is something that's really lovely and a lot easier to integrate. So let's create some space now that we understand what we're doing. And so we're going to define our integral, which I'm going to call I, as being equal to this sum from 1 to infinity of the integral from n to n plus 1 of x minus n over x to the 4 dx. And we could honestly just use power rule to integrate this, because if we simplify x over x to the 4, that's going to be x to the negative 3. And if we simplify negative n over x to the 4, that's just negative n, x to the negative 4 dx. And we're going to add 1 to the power and divide by the new power. So add 1 to negative 3 is negative 2, divide by negative 2, it's going to be negative 1 over x squared. Add 1 to the power is negative 3, divide by that power is going to be plus n over 3 x cubed. And this is between the bounds of n plus 1 and n. So let's sub in our values. Let's sub in our upper and lower bounds. We're still summing from 1 to infinity. Our lower bound is negative 1 over n plus 1 squared plus n over 3 times n plus 1 cubed. And we have to subtract the value of the integral from our lower bound. And it's going to be subtracting negative 1 over x squared, which is the same as adding 1 over x squared, except of course now it's n. And then we're going to subtract n over 3 n cubed. So the first thing you might be urging to do is that really nice cancellation there. And now let's group together our terms that have similar denominators. I'm talking about the n squareds and the n plus 1 squared slash cubes. Sorry, I've just noticed I actually forgot to write down my half over here, which means that we should have a 2 there and there. And that means that our nice common denominator here is probably going to be 1 over 6 times n plus 1 cubed. So if that's the case, we're going to have 6 n plus 1 cubed here. And to get that denominator for this fraction, we would have to multiply by 3 times n plus 1, or in other words, 3n plus 3. And here we'd only have to multiply by 2. And again, if we wanted to group these together, I think that 1 over 6n squared is probably our best bet. And so we're going to multiply by 3 and 3 here and 2 and 2 here, which means we're going to have plus 1 over 6n squared. Okay, great. Now let's just do the cancellation that's necessary here. We're doing minus 3n plus 2n minus 3, which is going to be minus n minus 3, or we can pull that negative out of the whole fraction and have an n plus 3 on our numerator. Okay, great. So we're getting into some territory that looks like it might be more familiar, specifically over here. So I'm going to make some more space, because I always think it's important that we can see what we're trying to calculate. And I'm going to rewrite this, but I'm going to split our sums up, because that's going to make things a lot easier for us. So we're looking at I being equal to 1 over 6 times the sum from n equals 1 to infinity of 1 over n squared, minus 1 over 6 times the sum from n equals 1 to infinity of n plus 3 divided by n plus 1 cubed. So a lot of you may realise that this sum here is very familiar. It's known as the Basel problem, the sum of the reciprocals of the squares. It was calculated by Euler, which is why it's named after his hometown of Basel, and it's famously equal to pi squared over 6. So we already know how to deal with this half of our integral. It's just going to be pi squared over 36, because we've got to remember to multiply by a 1 over 6 over here. So what about the right-hand side? Well, I kind of like the look of this fraction, because it's looking like it might be quite easy to deal with. But I don't like the fact there's an n plus 1 here in the denominator. It would be so much easier if it was a term that didn't have anything added to it, because as soon as we start adding things, we end up with binomial expansion and it gets a lot more complicated. It would be so nice if we could have a variable k that would just equal to n plus 1, so that we didn't have to deal with this adding. And there's nothing stopping us from defining that. So let's rewrite our our sum. Now when n starts from 1, k's got to be 1 bigger than that, so k is going to start from 2. And of course infinity plus 1 is still infinity, so we still end at infinity. In the numerator here, what we've got is n plus 1 plus 2. And so given that n plus 1 is k, our new numerator is going to be k plus 2. And our denominator here was n plus 1, which is now k. So we're going to replace that with k cubed. Okay, this is looking great because there's going to be some nice cancellation here and we can start splitting these up into two individual sums as well. So let's just rewrite everything that we've done so far. That's pi squared over 36 minus 1 over 6 times the sum from k equals 2 to infinity of k over k cubed, which is just 1 over k squared. And then we're going to do minus 2 over 6, which is also known as minus 1 over 3 of the sum from k equals 2 to infinity of 1 over k cubed. Okay, great. So now we have our entire integral just in terms of sums of reciprocals of various powers. And so this should be calling to mind a function that you may have come across before, known as the zeta function. And I'm horrible at writing zetas, and this is a horrible attempt, but there we go. Zeta of x is defined as being equal to the sum from 1 to infinity of 1 over n to the x. So we can clearly see that the problem we looked at earlier, the Basel problem, the sum from 1 to infinity of the reciprocals of the squares, is equal to zeta of 2, because that's when we're summing 1 over n squared, and we know it's equal to pi squared over 6. The sum of the reciprocals of the powers of 10, so 1 over 1 to the 10 plus 1 over 2 to the 10 plus 1 over 3 to the 10 on to infinity, would be zeta of 10. This sum here looks very close to zeta of 3, except we're just starting 1 higher than we should be. And similarly, this is very similar to zeta of 2, we're just starting 1 higher than we should be. But the first term in any integer value of the zeta function's always got to be 1, right? Because this sum here from 2 is going to be 1 over 4 plus 1 over 9 plus 1 over 16 off to infinity. The only difference between that and starting from k equals 1 is that if we start from 1, we've got 1 over 1 over here. And the same can be said about k cubed. So let's rewrite this. What we're looking at is pi squared over 36 minus 1 over 6 times the sum from k equals 1 to infinity of 1 over k squared, but minus that 1 that we don't want. And again, over here, we're looking at the sum from k equals 1 to infinity of 1 over k cubed minus that 1 that we don't want. And so now we can express our answer in terms of the zeta function. This one we don't have to, because we know that that's equal to pi squared over 6. Zeta of 3 is also equal to a constant. I think it's just bigger than 1. And it's called Apéry's constant because it was found by Apéry, but we don't really need to worry about that because I'm just going to write my answer in terms of zeta. And again, apologies for my horrible zetas. So we're basically there. Let's just finish expanding this. We've got pi squared over 36 minus pi squared, oops, I should say 6, over 36. So they're going to cancel. There you go, all our work with zeta of 2, and we don't even need it after all. Plus 1/6 minus 1/3 times, oh dear, that was really bad, zeta of 3 plus 1/3. All right, so this is it. This is our big reveal. We've had some nice cancellation here. You guys may note that 1 over 6 plus 1 over 3 is a half. So the value of our integral from 1 to infinity of x minus the floor function of x over x to the 4 dx is just equal to a half minus 1 over 3 times Apéry's constant, or the zeta function evaluated at 3. And I thought this was a really nice integral because it shows you the discrete properties of the floor function. It allows us to practice doing some infinite sums. It allows us to kind of come into contact with the zeta function in quite a friendly way. And it involves a really nice first step that's quite satisfying. So I hope you guys enjoyed. Please let me know if there's any topics you want me to cover next. Thanks for watching.